So you're a physics student and you got another test coming up. What are you gonna do about it? You're gonna review. That's right. Test 4, just like all the other tests, will give you 90 minutes. You'll have the full lab block to work on this thing. It'll consist of 15 multiple choice questions, each worth 2 points. One diagram, rather than a lab-based question, since most of our labs have just been observational, I've decided to just go with a diagram for you to fill out and label. And 5 free response questions, all 10 points. Just like every other test this year, feel free to bring yourself one sheet of paper front and back, and you're going to need to provide a calculator that's not your phone or otherwise can't connect to the internet. Let me know ahead of time if you want to borrow one. I will have one waiting for you with your name on it. So let's dive straight into this content. Charge. Charge is one of those just properties of matter, kind of like mass. It's just something that matter has. Positive charge is provided by protons. Negative charge is provided by electrons. Now, the charge of one single proton and the charge of one single electron is the smallest little unit of charge that an object can have. This is called the elementary charge, and it has a value of 1.6 times 10 to the negative 19 coulombs. So every single proton provides 1.6 times 10 to the negative 19 positive coulombs. Each electron provides negative 1.6 times 10 to the negative 19 coulombs. They've got the same charge, but way different masses. Protons are way, way, way bigger than electrons. Meanwhile, neutrons are just hanging out. They're neutral. They've got no charge. Boring. A couple of other things about charges that you must not forget. One, all charge is quantized. Basically what that means is I could have an excess of 1 electron, or 2 electrons, or 3, or 27 million, but I'm not going to have an excess of 1.5 electrons. So every single charge in coulombs is going to be an integer multiple of that elementary charge. I could also have a deficiency of 1 electron, 2 electrons, 3 electrons, 2.7 times 10 to the 12th electrons, but I couldn't have a deficiency of 7 2/3 electrons. Additionally, all charges are conserved. This is why if I've got a neutral object and a positive object and I touch them together, they're not going to both be neutral because there aren't enough electrons to go around to make them both neutral. They will try to spread evenly as possible, but charges are overall conserved. The only way that an object can become charged or become neutral is to transfer electrons from one place to the other. They're not just going to appear out of nowhere. And in a closed system, meaning nothing is connected to ground, and there's no way for electrons to flow in and out of the system, then the total charge is going to stay constant. Then we got a little bit more quantitative with it and started looking at forces. The force between any two objects with charge can be found with Coulomb's law. That's F equals K times Q1 times Q2 all over R squared. Here, Q1's just the charge of object 1, whatever that might be, and that's going to be measured in coulombs. Q2 is the charge of object 2, and that's going to be measured in coulombs. R is the distance between the two objects, and that right there is going to be measured in meters. And F is the force that each experiences. Do not forget to convert all these values to base units. A lot of times I'm going to give you distances in centimeters or millimeters or micrometers. A lot of times I'm going to give you charges in nanocoulombs, microcoulombs. So be very familiar with and very comfortable with converting these metric prefixes back to base units. Be sure that you know how to at least interpret the triboelectric series. Objects that are further up the positive side, it's not necessarily that they're always positive. It just means that if they rub against something lower down the list, then they will become positive. Similarly, something lower down the list, if they rub against something higher up the list, they will become negative. So for example, if I rub polyester and, let's say, cotton together for whatever reason, the cotton will become positively charged, and the polyester will become negatively charged. That means the polyester will take electrons from the cotton. But If instead I rub, let's say, polyester with silicon, the polyester will become positively charged because it's closer on the positive end of the spectrum than the silicon is. The silicon will become negatively charged, so basically the polyester will give up electrons to the silicon. Then there's grounding. You've got to know what grounding is. It's basically connecting something to an infinite reserve of electrons. The way I like to think of ground is it's always neutral, and there are so freaking many electrons that it can handle giving some up or taking some in, and it still stays neutral. It's basically something outside of any system where electrons can freely come and go if they're connected. You can use it to discharge an object. Basically, if I've got a really positively charged object, connect it to ground, electrons from the ground are going to hop on that positive party, and it'll become neutral. If I got a negatively charged object, and I connect it to ground, all these electrons really don't like being near each other. Each and every electron thinks the other one's nasty. So they hop on the grounding wire and they go straight into the ground. It can also be used to charge an object. And you're going to see this a lot with the process of induction. When you use induction, sometimes you'll connect objects to the ground, and electrons will pile on to a neutral object if it's near a positive object, because it senses that that entire system up there is positive. Or, if a neutral object is near a negative object, and the neutral one is then grounded, electrons on the neutral one will flee into the ground to get away from all those nasty little electrons that are nearby. In either case, you're taking a neutral object, and you are either throwing electrons on, making it negatively charged, or taking electrons away, making it positively charged. There's a lot of confusion sometimes here. Insulators and induction are not the same thing. Induction is a process, while insulators are types of objects. Not only that, typically induction is used on conductors. Induction isn't really used on insulators all that much. So just because they both start with IN, they are very different things. Induction is charging a conductor indirectly. Insulators just don't allow electrons to freely move around. Other than that, they're not very different. An insulator can be neutral or charged. Think about how I took that balloon and rubbed it on my head and stuck it on the wall. That was a charged balloon, but rubber's a really good insulator. A lot of times they're charged with rubbing. And once they get charged, they stay local to where the charge happened. So when I rubbed the balloon on my head and stuck it to the wall, when I tried to turn it around and stuck it to the wall again, then the balloon just straight up fell off. Conductors, meanwhile, can also be neutral or charged. Think about that aluminum sphere that makes up the Van de Graaff generator. That was definitely strongly charged, and sometimes it's neutral. It can be charged with conduction and induction, again, not insulators. And it allows these electrons to freely move throughout. Once it gets charged, electrons will distribute evenly over the surface. This is where I took a bunch of you all, made you pretend to be electrons, roped out a spot on the floor with red rope, and then yelled, "Go!" And you all repelled each other to the outer edges. So, with conductors, electrons distribute themselves across the surface. Another term you need to know and be aware of is polarization. Polarization is a separation of charge, and both insulators and conductors can be polarized, but in different ways. A conductor can be entirely polarized, which means all the free electrons can go to one side or the other, leaving behind a net positive charge. Don't forget, positives don't move. The protons are stuck at the center of their atoms in the nucleus, so they're not going to be moving around. However, if electrons leave a region of a conductor, then they leave behind an overall positive charge because the protons are still stuck there. Meanwhile, insulators can be atomically polarized. While electrons are not free to move to the far side of an insulator, they're free to move to the far side of their little atoms. This is why when you stuck the meter stick on the corner of the table, charged up a Teflon rod, the meter stick swiveled toward the rod. This was because the little atoms in the meter stick were getting polarized with the opposite sign charge closer than the like sign charge of the rod. Because it was a little bit closer, it was attracted. Couple of different ways to charge conductors. One is by conduction. This is charging by contact. So conduction, contact. Induction is an indirect. Conduction, contact, induction, indirect charging. And remember, induction and insulators don't go together. Basically, you just take one charged object, bring it into contact, and electrons just transfer one way or the other. With conduction, they're free to move throughout both objects that are touching. Induction is a little bit different. Let's go through some of these images. So once again with conduction, if I've got a negative object, a neutral object, make contact, electrons move from one to the other. Conduction's a great way to get two objects of equal type charge, so either both negative or both positive. Here's an example of a positive object touching a neutral object. Electrons will flow from neutral onto positive, and now they're both positive. Induction is a great way to get two objects oppositely charged. If I bring a negative near a neutral object, ground the neutral object, electrons will escape away from that nasty negative and into the ground. When I take away the ground and take away that negative object, then all that's left is a positively charged object. The thing that used to be neutral lost electrons, now it's positive. I don't even have to use grounding. I could have two objects that are just touching each other, two conductors. When a positive object comes nearby, they both get polarized, except because they're both conductors, the electrons are free to move from one to another and all pile up on sphere A over here, leaving behind a net positive charge on sphere B. Separate them, and ultimately what's happened is A used to be neutral and electrons hopped on. It became negative. B used to be neutral and electrons left. It became positive. So induction is a great way to get opposite style charges. After we got through all this fun mess between forces, conduction, induction, we started talking about electric fields. Now, electric fields basically point at a spot in space and say, how many newtons would a little positive charge feel right here? It's measured in newtons per coulomb, which literally means if I stick a charged object in this spot in space, how many newtons of force will it feel for every coulomb of charge that it brings with it? Because the convention just has us treating electric fields as if a positive charge were nearby, it points toward negatives, because positives and negatives are attracted to each other, and it points away from positive, because positives and positives repel. At the end of the day, you can find an electric field from some source. You have to have some charged object as the source of the electric field. And that equation will be just K times Q over R squared, where Q is the charge of the object creating the field, or the source charge. E is just the electric field in newtons per coulomb. R, again measured in meters, is the distance away from the charge where you want to measure the electric field. And K is good old Coulomb's constant, 9 times 10 to the 9th. Now, if you have multiple charges, you're going to get a kind of funky shaped field. This is because at every single point, if I call this blue negative charge Q1, and I call this red positive charge Q2, at every single point, I'm going to have to find what is E1 plus E2 at this point. Oh, and by the way, both of these electric fields are vectors. So I need to figure out which way is E1 pointing, the electric field just due to Q1, which way is the electric field just to Q2 pointing, E2, break them down into X and Y components, and vector add them. Fun. If you got two negatives, it's the same thing, except now both sources have the field lines pointing toward them. And same deal with two positives, except both sources have field lines pointing away from them. Then we talked about special cases called capacitors. Capacitors are great little objects that are designed to build up and release charge quickly, store energy, all that kind of good stuff. Within a capacitor, the electric field lines are perfectly straight from the positive plate to the negative. When you get to the outside edge, it starts to look like that dipole shape again, bending around this way. Within a capacitor, you have two different plates. One is positive Q, one is negative Q. They happen to have the exact same charge, the same magnitude charge, but opposite signs. And we'll get to capacitors more in just a little bit here. So a couple of rules when you're sketching these lines. One, the field lines only start on positive charges and they only end on negative charges. Typically, where the field is stronger, you're going to have more lines coming off of it, but I'm not going to focus too much on that on this test. Field lines never cross. They can't really. You can't have a point in space that has two different directions of total force. There's only one direction of total force. And electric field lines are vectors, so anytime you add up multiple sources, treat them as vectors. Meanwhile, we've got voltage. Right? Now, voltage is kind of like an electric field, except instead of the force that a charged particle would feel at this point in space, it's all about the energy that a charged particle would have at this point in space. So voltage, measured in volts, is the same thing as the potential energy per coulomb of charge. So joules per coulomb is a volt. Just like with electric fields, there have to be source charges that create a region of voltage around it. To calculate the voltage away from one of these source charges, you just use K times Q over R. K is good old Coulomb's constant, 9 times 10 to the 9th, and I'll give that to you on the test as well. R is the distance away from the object you want to measure the voltage, and Q is the source charge in coulombs. You did a lab on equipotential lines. These are different from electric field lines. Electric field lines show the direction that a charged particle would feel a force at every point in space. Equipotential lines indicate regions of that space where a charged particle would have the same amount of potential energy. Think of it like lines on a topographic map. Every line on a topographic map indicates constant elevation, which means constant potential energy. The closer together those lines are, the steeper the hill. I like to think of positive particles as the peaks of hills. I like to think of negative particles as the bottoms of sinkholes. You can indeed have negative voltage if you've got a negative particle that's creating it. Let's talk a bit about vectors versus scalars. Forces and fields are both vectors. If you encounter a force and a field, then forget about the negative at first. Just throw in absolute values of Q, solve whatever you're trying to solve, the force in newtons or the electric field in newtons per coulomb, and then figure out separately from that magnitude which direction it's going. Likes repel, opposites attract, and treat the E field as if it's a little positive charge everywhere. Scalars include energy and voltage, and charge, and whatever else. They do not have direction, so don't ignore negatives for Q. A negative charge produces negative voltage nearby. The nice thing about this is you don't have to worry about X and Y components. You simply take the voltage from source charge 1, the voltage from source charge 2, the voltage from source charge 3, and add them. Don't worry about breaking them into X and Y. Don't worry about pointing right or left. Just add the numbers. Nice. I started talking a bit about capacitors and then went off in a different direction, so let's come back to that now. You've got one plate of plus Q, one plate of minus Q. Now this value of Q is what's used in this equation. Don't get confused. Just because there are two plates doesn't mean I need to double this value. Like let's say this is 2 coulombs, this is negative 2 coulombs. I would just use the number 2 in this equation. I wouldn't double it to 4, I wouldn't square it to 4, or anything like that. Wouldn't add them to 0. It's just 2. Q is the magnitude of the charge on each plate individually. Because one is positive and one is negative, there's going to be a difference in voltage from one plate to the other. This depends on the electric field strength. We talked in class about how newtons per coulomb is the same thing as volts per meter. So it depends on the electric field strength and the separation of these two plates. But there's going to be a change in voltage. The capacitance is defined as the ratio of the charge built up on a plate to its voltage. So capacitance is measured in farads, and a farad is just a coulomb per volt. Capacitance is what the manufacturer will tell you when they give you a capacitor. That's its rating, basically. And the amount of energy that's stored in a capacitor in joules, energy is always in joules, is going to be 1/2 times Q times V. Now, since Q equals C delta V, if I wanted to find an equation that involved capacitance and voltage and gave me energy, that would be 1/2 times C times V times V. So 1/2 times C times the change in voltage squared will also get me the energy in joules. All right, make your cheat sheet. Let me know what questions you have. Take a look at last year's test posted on Canvas, and good luck.